Okay, ma'am.
So,
Ma'am,
am I
last,
audible?
yes, ma'am, you are audible, ma'am.
Yeah. Last class, what we did?
Ma'am, we started on non-parametric classifiers examples. First, we saw k nearest neighbors. Then we saw about support vector machines and its
Okay.
clearance parameters. Then what is a kernel and kernel trick. Then we read about decision trees, ma'am.
Okay. What we did in the decision trees?
Ma'am, in decision trees, first we saw how to build what is a basic decision tree. Then you explained with giving the family example. Then we saw about bushy tree and binary tree.
Then we saw how to
Then
split the nodes. Yeah.
yes, ma'am.
Then,
Then information gain and this Gini impurity we saw, ma'am.
okay. Very good. Chain and Gini impurity or the quality measures to test a node.
Yes, ma'am.
So we did three non-parametric classifier. In today's class, what we will do is that we will start off with the parametric classifier, one example for parametric classifier, and we will see about ensamples of the classifier, how to do with that. So, so what is a parametric classifier? Can anyone recollect? So non-parametric classifiers, they have in common that they learn directly from the data. But here, what we do, it learns from the parameters and also it makes about an assumption about the data. So parametric classifier makes an assumption and also it learns from the parameter. So what it has the name called parametric classifiers. So, so parametric classifiers yield quick results, though they are not most accurate, they yield quick results, though they are not accurate. So they are very fast and because they work, because they begin their assumption about the data. So today's we will see about an algorithm called naive based algorithm or classifier. So naive based classifier, it is a probabilistic classifier. It is based on Bayes theorem. It is called as naive because it assumes all features are independent features. It is a very important assumption that naive Bayes makes. All features are independent. This is rarely true in real world, but it performs very well in many applications. So we have studied about Bayes theorem, right? So what does Bayes theorem state says? So we did it when we are looking at the probability. When we are looking at the probability, we learned about Bayes theorem. So what it essentially states. So this is the formula which we learned for the Bayes theorem, right? So what is P of C given X? Let us assume C is the classes. So what we learned, P of C given X is probability of a class C given the feature X. It is called as a posterior probability. What is probability of X given C? Is its probability of the feature X given the class C. It is called as a likelihood. What is probability of C? It is probability of the class C. Or else we can call it as prior probability. What is probability of X? It is probability of the feature. Or else we can call it as evidence. So how do we, so this is the formula for the Bayes theorem. So how do we go on calculate the naive Bayes algorithm? So how does so first what we need to do is that we need to calculate the prior probability. So what is prior probability? We saw that it is the probability of the classes given the x's. So, sorry, prior probability is nothing but the probability of the classes. So we need to determine how often each class appears in the data set. So that is the prior probability. The second thing what we need to do is that we need to calculate the likelihood. So what is the likelihood here? It is a probability of the features of X given the class C. So we need to compute the probability of each feature knowing their classes. Then third, we need to apply the Bayes theorem. So Bayes theorem is that calculating the posterior probability. So we need to determine the probability of the class C given the input features X. So we have to identify what is the class C and we are calculating the posterior probability using the Bayes theorem. So finally, what we will do is that we will choose the class which has the highest probability. So this is how naive Bayes algorithm works. So why it is called naive? Because it makes assumption about the prior, and this prior is not based on the contents of the data. Since it makes assumptions about the prior, it is called as naive. That is, we are making an uninformed or naive characterization of the data. We just assume the data has some structure in this one. So if we are getting good results, we are right. If we are not getting good results, if the data is not matching, then we will have worse results. So most of the time, it assumes what to say. We will the assumption would be turned out to be correct enough. So what naive Bayes is so popular. The interesting thing is that we never do a justification for the assumption or if there is any formula to calculate if the assumption is true or not. We just go ahead with assuming that the data follows certain structure. So the most common assumption is that we assume that every feature of our sample follows Gaussian distribution. So if you recollect that the Gaussian distribution is nothing but a famous bell curve with a smooth and symmetrical shape. With a central peak. So this is our prior. So our assumption is that every feature of our sample follows a Gaussian distribution. And this assumption will be a good fit because majority of the real life data are Gaussian. So this assumption will hold good for most of the applications. Is it clear? We call it as naive because it makes an assumption about the data. We do not know what the data content is, but it makes an assumption about the data. Most of the assumption is that what is the assumption? Every feature of a sample will follow the Gaussian distribution. This is the assumption which we make is our prior. Is it clear? So how we calculate our naive Bayes algorithm is that we calculate the posterior probability, that what is the probability of the classes given the features. And then we choose the class with the highest probability to be our class of our input data. And we call it as naive because it makes an assumption about the prior. Our prior here is that the features follow Gaussian distribution. Let's take some example. Let us assume that you have two categories of data. One category is in pink color and the other one is in green color. So most of the examples which we deal are in are 2D data with two categories. So here this is a 2D data. It has two categories. 2D means two features. We will assume that all these samples are picked from a Gaussian distribution. So it is a set of 2D training data with a naive Bayes. So what it will assume is that, so if you take this pink data set, it is a 2D data set. So both its x-axis and its y-axis are coming from the Gaussian. So similarly, for this green data, it has two features. One is x-axis and y-axis. We assume that the x-axis is one feature and y-axis is another feature. So both the x and y for this data are coming from Gaussian. So if you try to fit a curve, a Gaussian curve around it, so we will get the best fit for it using 2D hills. So if I can draw here separately, this corresponds to this one. This corresponds to this one. So we can build a Gaussian distribution for both these points. And if you try to split the training data randomly, and then you want to split the training data to the test set, we can observe that the test samples will exactly fit this data. So this is happening because we have assumed that the data features are coming from the Gaussian distribution, or this data is sampled from a Gaussian. This distribution fits very well to the data. Let us assume that we are not, we are trying to sample from a distribution which is not Gaussian, or else our prior of the features do not follow Gaussian distribution. Let us assume we have a data like this. So we have a noisy half moon data. So these classes are not drawn from the Gaussian. Then how we can expect the naive Bayes to match them? So we can see what can we expect from that classifier. So here also the classifier, since it's a naive Bayes classifier, it will assume that though it is not from a Gaussian distribution, it will assume that it is from a Gaussian distribution, and it will try to fit a bell curve for both the curves. This is for the pink curve, and for the blue curve, it would be like this. It would try to fit two Gaussian. It will try to fit two Gaussian curves for these two clusters of data. When our Gaussian-based naive Bayes algorithm matches our half-moon data, it assumes the values of Gaussian because it usually assumes that the features are Gaussian. This is the best Gaussian fit it could provide for the data. So if you try to overlap here, what we can have is that we can have something like this. It is not a complete match of it. So it only partially matches. We are not surprised that there could be misclassifications of the data. It is only amazing that how well it can do it on the naive Bayes algorithm. So why it also has a partial fit, though it is not from the Gaussian. Why it has a partial fit means because majority of the real world data are Gaussian distributed, so it matches appropriately. So is it clear? So this is about naive Bayes algorithm. So now we can do a quick recap of all the classifiers which I've done, because we will be using these classifiers in our project. So now we will briefly look at the pros and cons of each classifier. So far we have looked four popular classification algorithms. So most of the machine learning libraries offer routines for these algorithms. So let us look at the first one, KNN. So this method is a flexible method. They doesn't explicitly represent the boundaries. They are fast to train because they are saving each training sample. So they are fast to train. But the predictions are slow because they have to search for the nearest neighbors. The predictions are usually slow. They consume huge memory because they have to save every training sample. They consume huge memory. If the training set is larger than the available memory, then what we need to do is that we need to typically start with the virtual memory. Whenever our training samples are larger than the available memory, we will start with the virtual memory so that it can save the samples. But whenever we use a virtual memory, what happens is that the algorithm will slow down. So this is about the pros and cons of the K nearest neighbor classifier. So the second classifier which we will look at is SVM. So what SVM does is SVM is slower in training. But they are much faster in predictions. They do not need much memory because here they are not saving the samples, but we are only saving the boundary. So they do not need much memory. So they use a kernel trick. So what this kernel trick is used? This kernel trick is used to find the classification boundaries that are much more complicated than the straight lines. So as the training set grows, the size of the training also increases. Then it uses a clearance parameter. Clearance parameter C, because this is sensitive to the quality of the result. So it specifies how many samples are allowed near the boundary. So the clearance parameter is used here. And we can use cross validation to choose different values of C and pick the best one. So this is about the pros and cons of the SVM. Next, we will discuss about decision trees. So the decision trees are usually faster to train, but they are also faster in making the prediction. So that is the reason they are used in most of the algorithms. They can handle weird boundaries between the downside is it is prone to overfitting. But decision trees are usually popular because they explain the way how a particular result has been arrived. So though they produce inferior results, since it is easy to comprehend by the humans, it is quite popular. Next, we will see about the pros and cons of naive Bayes. Naive Bayes. So here also training is faster. It trains quickly and predicts quickly. And also it is not too hard to explain the results. It has no parameters, so that we don't have to have an extensive search like in KNN or in SVM. It doesn't have parameters, huge parameters to tune. And then if you are working with a well separated data, it produces good results. So usually when we have large number of features, we might end up with the curse of dimensionality. But or here, when we have huge number of cases, features, the samples are well separated apart, and that would be a strength to the naive Bayes. So what people do is that usually they will first try with naive Bayes because it is faster to train and predict, and they get a feel for the data. So if the prediction quality is poor, then they move for an expensive classifier later on. So they first start with naive Bayes. And we can also see about some complicated classifiers later on with using deep neural networks because they excel at classification. They produce unprecedented accuracy. So deep neural networks are preferred ones, but these classifiers are used in everyday because they are well understood, and it is usually easy to comprehend because we can easily understand why a particular result are commonly used in everyday practice. Is it clear? Any questions?
No, ma'am.
So if you have if you have no questions, then we will. So far, what we have done is that we have seen the types of classifier, parametric and non-parametric, and we saw 3 examples in non-parametric and 1 example in parametric classifiers. For your projects, you can use select any of these classifiers or even other classifiers uh, in your research problem. Now we will go on to the next topic, ensembles. What does ensemble mean? Any idea? Anyone would like to come?
To
Yeah,
collect everything together.
fantastic. To collect everything together. So how we can apply ensembles here? So why we are talking about ensembles in classifier? So why we are wanting to talk is that we learned that some individual learn. So instead of classifiers, I'm using the term called learners. So some individual learners are usually imperfect. Sometimes they can yield incorrect results. So what we are doing is that instead of using a single learner, we are combining multiple learners so that they can outperform the single individual learner. So anyone can make mistake, even algorithm can make mistake. In case of doubt, what we are doing is that we are not running a single learner. We run the data through multiple learners with the differently trained multiple learners and then let them vote the final answer. There is one simple example I would like to cite. So in 1960s, Apollo spacecraft was launched in the moon. So they had 2 computers, one in the common module, which is orbiting around the moon, and another one is landed on the moon. So all these computers neither of them had backup. So those time it was built using integrated circuit, which was a relatively new technology at that time. In order to protect against the failure, every board was duplicated twice. So they had three boards which was running synchronously. We can call them as triple modular redundancy. So each output module was decided by the majority of the votes. It is not just by the single thing. We had three boards. So the majority of them was uh, used as the output, because they don't want to account for the failure, and because this failure shouldn't compromise the mission. So what they used two additional things. So two additional ICs. So sorry, two additional boards, not ICs. So here it is not a new technology of combining multiple learners. It has already been used in several missions. So in mission learning, what we are doing is that we used a group of learners called ensembles. So this Apollo computers is a general idea of multiple predictions from independent algorithms. So what we are going to do is that we will combine multiple learners and then take vote from every learner will have one prediction, and all these predictions are combined. So if it is a regression problem, we can aggregate the score and produce an output. If it's a categorizing problem, we can choose the majority of the prediction and use it as a final uh, final category. So this is the idea of ensemble. So why we use ensemble is that because it boosts efficiencies. It boosts efficiency. Many small, fast learners can be combined together, and it will produce result as equivalent to that of a one single big complex learner in a less time. So that is the reason we are going for ensembles. Ensembles we can otherwise call as family of learners also. We can call it ensembles or family of learners. So this is also common in human societies. In order to elect a leader, what we do, we cast vote to elect a leader. In political decisions are made by the boards, are made by voting. Even when a law is passed by the Senate, it is passed by voting. So voting is common in human societies also, not just in machine learning. In human societies also, it is common. Why we are using voting? Because the individual's bias or a judgment should not affect the final outcome. So what they do, we take the consensus from multiple individual learners. So to avoid the errors from the individual bias or individual behavior, we are taking, though it doesn't guarantee a good decision, it will avoid the problems on the bias made by the individuals. So the learning algorithms, what we are going to do is going to be trained. So what is the difference is that, so suppose imagine that we have individual trainers. So we have individual trainers like this. So if each individual trainer is trained by the same data, we are going to have the duplicate of the same thing. So that is not ensemble. So what we need to do is that every trainer will be trained by uh, different data. So let this data be X, let this data be Y, this data be Z. So every learner will be trained by a slightly different data set. So every learner is unique. So we will have a training data set. From the training data set, what we will do, we will randomly sample some data and train each individual learner. By training each individual learner, we get a different learner and then we get the predictions from them. So based on the regression problem or a classification problem, we get the final output. Because in machine learning, it has a profound impact, because it is used in evaluating the home loans or in a business to determine the admission to college, pre-screening job applications. So it has a lot of applications. So if there is a bias in the training data, that bias will be reflected in the final decision also. So one way to avoid this problem is to train multiple learners using different training data set from different sources. So this will avoid the systematic bias and it will influence the final data also. So Supposing if you are using weather forecasting, the weather forecasting can often come from the same model many times with a slightly different. So all these learners are the same learners for weather forecasting. But what you do is that you give a different initial stating condition for everything. So same data, same learner, but different initial conditions. So it becomes a different learner. And finally, what you do is that you collect all the predicted outcomes and you select the best out of the predicted outcomes. So this technique is called as ensemble forecasting. So are you clear with the ensemble technique? So the what does the technique does is that you create multiple learners with different training data. Not with the same training data. We are not creating duplicates. With different training data, you are creating multiple learners. And then we select the most frequently predicted outcome. This is the process involved in ensemble. Is it clear?
Yes, ma'am.
So next we will learn about voting.
Hello, ma'am.
Then we have, yeah.
Does all learners will use the same algorithm to classify, or each one has different algorithm?
That depends on your what to say. Suppose if you are using decision trees, we can use everything as decision trees. But suppose if you want to use one learner as SVM, another learner as decision tree, that is also possible. But what is made sure is that they use different data because they will have different or else different starting conditions.
Okay, ma'am. Okay.
But mostly we will use the same learners. As of I have used the same learners for same learning algorithm, but different
Okay,
data set.
ma'am. Okay. Thank you.
So where we are. So we can learn about voting. So when we have multiple results from multiple learners, we need to somehow come up with a final single answer. So what is a way of doing is plurality voting is one way of getting the final single outcome. So what is plurality voting is that so the final prediction maybe will be the one which receives the most vote. We can opt them as a winner. Or otherwise, suppose if what happens if ties comes. If ties comes, we can either re-vote or else what we can do is that we can randomly select one as the final entry. So this can be done. So plurality voting is the output prediction receives the most vote. In case of ties, we either re-vote or randomly select the winner from the tiebreakers. So plurality voting is really easy to understand and implement because it is usually a sensible result. Though it is not a perfect one, in social context, it is commonly used. So we can also use weighted plurality voting. So what is weighted plurality voting is that every vote gets a certain weight, which is just a number. So if, for every vote, we will give you a number. Suppose imagine that we all begin with the score 0. Score 0 for a cast. For a category A, we start with the score A. Suppose if we have the weight of +4, then A will get the weight of from 0, it will shift to +4. Now there is another another learner which is giving the weight of minus 1.5. So now what will happen? A will get the value of 2.5. So similarly for all the categories, for B there will be some weight, for C there will be some weight, for D there will be some weight. For all the categories there will be one weight. So whichever has the largest number after adding will be the category for the particular problem. Is it clear? So this is about plurality weighted voting. So now next we will see about a popular type of ensemble. We are talking about ensemble. So far what we did, we got the idea of ensemble and we got the idea of voting in it. So ensemble means using multiple classifiers, multiple learners, using different training data from different sources or from the same source. So how to do this ensemble? So there are two types of ensemble. One is called as bagging and other one is called as boosting. So now we will see about bagging. So what is bagging? So it is a popular type of ensemble. It is made out of decision trees. It is usually fast for both training and prediction. So decision trees can be used for both categorization and regression. Here we will focus only on the categorization variety. So there are two popular techniques. How to bundle this decision trees into a larger group. So that they can significantly outperform the individuals. So we know ensemble is multiple learners. So how to make this multiple decision trees? So here the learner is decision tree. So how to make or how to combine different decision trees is what we are going to see now. The core idea is we need to collect the decision trees that are slightly that are trained with different training sets. So they are not duplicates, they are similar, but they are different from each other. So when each sample goes, it will go through individual trees and then the final prediction will be collected from all the trees and the most popular prediction will be the output of the ensemble. So this is the criteria. So what is bagging here is that, suppose imagine that we have 8 samples like this. So these are not categories. To represent individual samples, I have given alphabets to them. So what we can do is that we can bootstrap these samples. You know what is bootstrapping, right? Bootstrapping with replacement. So there are two types, with replacement, without replacement. So here what we are doing is that with replacement, we are collecting 4 samples. So these are 8 samples. So we are bootstrapping 4 samples. So another set of 4 samples is, this is with replacement. So what happens with replacement? We can pick the same sample more than once. So since we are with replacement, here I have picked D twice. So even if you have picked G here, you can pick G here. So here I have picked F twice because we can pick the same sample multiple times. So what we will do is that, so this is our sample data. So from the sample data, we have created smaller sample data sets. So here we have here we have prepared 3 data sets. So using each of these training data sets, so here you can develop the first decision tree. Here you can build the second decision tree. Here you can build the third decision tree using this sample alone. So using different data sets, we are building the decision trees. So is it clear? So we create one decision tree for each bootstrap. We train the tree using the samples of these bootstrap. So if it's a regression problem, what we will do is that we will average all the predictions. So we will add the average the predictions from decision tree 1, decision tree 2, decision tree 3. So we will take all the 3 predictions, average it, and that will be the final outcome. If it is a classification problem, what we will do is that we will use the votes in the plurality election and we will produce the either a winner or a tie. So we will treat the individual classes. So we will do the plurality voting and elect the winner. So how we can do that? So a new sample arrives. So this new sample is given to 5 trees. So A will be the outcome of the first tree. B will be the outcome of the second tree. Class C will be the outcome of the third tree. Again, D will be the outcome of the fourth tree. So these are all different trees. So what we have done, the training is over with the individual, with these bootstrapping samples. After that, when a new sample comes to each of these trees, each tree will predict one class for the new sample. So now we can plot a histogram. So category versus number of votes. So A has got only 1 vote. B has got 2 votes. C has got only 1 vote. D has got 1 vote. So the majority of the the majority of the votes is obtained for sample B. So sample B is the outcome. So this is how this testing is done. So if you look at here, we need to come up with 2 parameters. So what are the 2 parameters which we need to fix? One is the, excuse me. Hello. Yeah.
Yes, ma'am.
I'm in between the class. Can I call you later? Yeah. Okay. Yeah. Any questions? Am I audible?
Yes, ma'am.
So do you have any questions?
No, ma'am. No, ma'am.
Okay. So if you look at here, we have to fix only 2 parameters in this bagging. So what we have to fix is that the first is the number of samples. So the number of samples which we are going to bootstrap, that is the first parameter which we are going to decide. The second is the number of trees. So the number of trees you want to build. So this is the second parameter which we need to specify. So the first thing is how many samples. The second thing is how many trees. These are the parameters which we need to fix. So is the process of this type of ensemble is clear? This type of ensemble is called as bagging. So next, we will learn about one concept. This concept is called as law of diminishing returns. So this concept is popular in economics. So what is this in economics is that suppose you imagine you have an input and an output. So this is the total input. This is the total output. So what will have during the productive phase when the input increases, the output also will increase. This phase is called as productive phase. Then what happens? It gets saturated, and after at some point it will start declining or start decreasing. So this phase where it starts to get saturated is called as diminishing returns. And after some point, it starts to decrease. When the input increases, the output will start to decrease. So this period is called as negative returns. So this is the concept which is used in economics. So when one input is there in the production process involved, so what happens? The output will eventually decrease. When the input increases, the output will eventually decrease. So how we can use this in machine learning if you look at it? So adding more number of classifiers can provide better prediction, but only till certain point. After a certain point, what will happen? If you increase the number of classifiers, it may not produce better results. So this is called as law of diminishing returns in ensemble construction. So the rule of thumb is, so the number of classifiers should be equal to the number of classes or categories. So this is the rule of thumb which we use. So we can use cross-validation to search for the best number of trees we want in a given data set, but usually the number of classifiers matches the number of classes. Sometimes if you look at even in our example, we would have not used the number of classifiers equal to the number of classes, but in machine learning, everything is based on trial and error. So we use it and we use cross-validation to come up with the good number. So is it clear? So if this is clear, then yeah. Any questions?
No, ma'am.
Okay, if this is clear, then we will go to the next concept, random forest. So random forest is a type of, yeah.
Ma'am, in voting, you told that we can do weighted voting now, ma'am.
Yes.
How do we assign weights? Like, on what basis we will assign weights?
So every classifier you can give some weights.
Okay, we are assigning it manually.
So for every category, you can assign weights. There are routines in machine learning libraries to attain some weights. But if you want more, suppose you want to weight one category at the highest level and another category at the lowest level, you can assign. That is based on the weights.
Okay. Okay. Thank you.
Yeah. So now we will go on to the next classifier, random forest. So random forest is based on the ensemble of decision trees. So it is also based on the concept of bagging. The trick is that how do we build our trees during training? That is what we are going to see in random forest. So the concept is same. So whatever we have used in the ensemble concept is same. The bagging concept is same. So the bagging concept, what we have our samples and we bootstrap those samples, and from each set of samples we build a tree. This concept is same in random forest. But how are we going to build the tree? That is how it has a special name, random forest. So usually what we did, if we previously saw in the decision tree, when we have a node with using some feature, we split the node into two. So based on the test of the individual features, we test we split the node into two, and the elements will be directed to the one child or the other child. So how we want to choose the features there, and that also we will see. So let's take one simple example. Let us assume that We have 5 samples. And we have 5 features. F1, F2, F3, F4, F5. So we have 4 samples and 5 features. What we will do usually is that, so how are we going to select the features? We know that in decision trees, a node will come and the node will have a test. So test on the feature. So based on the test on the feature, it will split the node into 2 children or whatever amount of children. So it will split the node based on the test on the feature. But how do you select that feature? So that is the question. So what random forest does is that it will select the features randomly from the set of features, because we are not going to use all the features. Either we can use all the features or we can select some features from it. But how are we going to select? So we are going to select it randomly. So for example, we can select F1, F4, F2. In another set of process, what we can select is that we can select another set of features, F5, F1, and F3. And from this group, from this randomly selected group, we can select a new rule based on F2. So we are determining which feature to use when splitting a node by feature bagging. So why it has got the name random forest is, so we use the name random because we randomly select the features at each node. We use the term forest because it is resulting in the collection of decision trees. So it's a collection of decision trees. So collection of trees is called as forest literally. So here we call it as forest because of the collection of decision trees. So every node is splitted based on the feature, and how we select the feature by randomly selecting those feature groups into a small sample set, small feature set. From the feature set, we pick one rule. Based on that one, we create the test for the node to split into children nodes. So here also, if you look at, there are 2 parameters to specify. So one parameter is the random selection of samples. Second is the number of trees we want to build. We often specify a percentage for this, but in machine learning libraries, there are a variety of mathematical formulas to calculate the number of features. So we can use any one of those. So is it clear? So the 2 parameters which we will specify is the random selection of numbers which we extract in each bootstrap, and the number of trees which we want to build for our algorithm. So these are the 2 parameters which are used in the random forest. So is it clear? So random forest uses the principles of bagging. It also uses an example of decision trees. So all the concept is similar, but only what is different here is that how are we selecting the feature set for splitting the nodes, is that is different, and it is called as forest because it's a collection of trees. We don't use different learners. For random forest, we will not use SPM. We will use only decision trees. So the classifiers here are decision trees. So that is the reason it is called as random forest. So there is one more concept called as extra trees. It is called as an extra tree because it has one more randomization step. Here we saw the selection of features is random. We will use yet one more randomization step to this one. So what is the step is that, so when making the decision trees, so one time to split the node, we find the random features, and then based on the feature, we select, we make a rule, and then we split the node into two children. So, and we can evaluate how best it is working. So sorry. So here, when we have a node, we select the random set of features. So we select the random set of features, and using these features, we fix a test. And with the test of those features, we divide the sample into two nodes. Sorry, we divide the node into two children's. So we can evaluate what is best using the information gain or Gini impurity. So one more randomization step here is that instead of splitting the point for each feature, we split the point randomly. So instead of using a feature to split, we are splitting it randomly based on the values that are present in the node. We split it randomly. So this is the randomization step which we are using. We choose to split the nodes randomly. Randomly based on the values that are present on the node. So this change in the ensemble is called as extremely randomized trees or extra trees. Although it might look like we might get worse results, but we know that decision trees are prone to overfitting. So it helps to avoid overfitting. So though it gives worse results, because of this random choice, we have to pay some accuracy. So what we have a trade-off between the accuracy and the overfitting. It reduces overfitting, so we compromise slightly on the accuracy. So is it clear? So the extra trees, we have one more step of randomization where instead of picking the features, we randomly split the node at a certain point. So, so based on the values, we split the node. So this is the randomization step added. So this is called as extremely randomized trees or extra trees. Why this is done? Why this randomization step is done? To avoid overfitting. So though there's a compromise in the accuracy, since it reduces overfitting, in some cases where we use extra trees instead of random forest. So is it clear? So what we have done today is that we started with an example of parametric classifier, which is called as naive Bayes. It makes the assumption that all the features are independent, and it also makes a popular assumption that the features follow the Gaussian distribution because most of the real world applications are Gaussian distributed. So naive Bayes algorithm is a probabilistic classifier. It is based on Bayes theorem, and we saw what is a Bayes theorem. We recollected that one, and we saw how naive Bayes algorithm work, and we also saw how it works when the data is sampled from the Gaussian distribution, how it works, and when the data is not sampled from the Gaussian distribution. So we saw both the cases, and then we analyzed the pros and cons of KNN, SVM, decision trees, and naive Bayes. So though neural networks are popular, these algorithms are commonly used because of they are easy to understand and they are relatively fast. So that is the reason, and they may not need as much as data which we need in neural networks. So that is the reason they are popular. Then we started with the concept of ensembles, and we learned what is the concept of ensemble, and then we learned what is voting. And one type of ensemble is bagging. there are two types of ensembles. One is bagging and boosting. Today we saw one type, which is called as bagging, and we saw how we train in bagging and how testing is done in bagging. And this is applicable for both the classification problem and regression problem. Then we saw what is called as law of diminishing returns in ensemble construction. This is the concept used in economics, but we have seen it in machine learning. And then we used we tried to understand bagging using one classifier called as random forest. And in random forest, why we call it as random forest, because it uses all the principles of bagging and ensemble classifier. And we also saw a variant of random forest, which is called as an extract trees. So is it clear? Any questions? So if you have no questions, then we will meet in the next class. I would like to make a small announcement on Sunday. We have a tutorial session from 10 to 12. So all of you, please bring your laptops. We will have a MATLAB tutorial session on Sunday in the department, in the conference room. I will make an announcement in the WhatsApp group also, but try to make it possible to attend this session. Yeah. Thank you.
Thank you, ma'am.
Thank you.